In this video, we'll classify the groups of order p squared where p is a prime. This will require knowing Lagrange's theorem, group actions, and specifically the orbit stabilizer theorem. Let G act on itself by conjugation. The conjugacy classes of G partition G like so. G is the union of distinct conjugacy of the elements in G. By the orbit stabilizer theorem, we need to have that the conjugacy class divides the order of the group p squared. So either the conjugacy class is of size 1 or p divides the size of the conjugacy class. Note that if some element z is in the center, then the conjugacy class of z is going to be 1. So the center's conjugacy classes are all distinct for each element. Therefore, we have that the order of G is the sum of the sizes of the conjugacy classes in the center plus the sum of all the other conjugacy classes, which must have p dividing it. P divides the order of G and this right hand side. So taking this equation mod p, we get that 0 is the size of the center mod p. In particular, this can't be of size 1, and therefore the center must be a non-trivial subgroup of the group. Therefore, the center must have size p or p squared. Now consider the quotient of G by its center. This is going to be a group of order either p or 1 by the above. So it's going to be a cyclic group. So G quotient by z, I'll just abbreviate the center as z for now, is going to be yz for some y in G that's specifically not in the center. Take G and H in G, then GZ is YIZ for some I, and similarly H is YJZ for some J, because of the group being cyclic. Thus, GH equals YIZ1, YJZ2 for some Z1 and Z2 in Z, which is going to be YI, YJ, Z1, Z2, since Z1 and Z2 are in the center, so we get that commuting. And YI and YJ commute because they're just powers of the same element. And similarly, Z2 and Z1 commute because they're in the center. Swap YI and Z2 again because it's in the center, and we get HG. Therefore, this group G is abelian. Now, by Lagrange's theorem, any G in G will have order 1 p or p squared. We now have two possibilities. Suppose there is a G in G such that its order is p squared. Well, if we have that, then the subgroup generated by G is a group of order p, and therefore it is the whole group G. Therefore, G is isomorphic to the cyclic group of order p squared. G does not contain an element of order p squared. Then we know that there must be some G that has order p, because it can't just there's only one identity element. Then consider the subgroup generated by that, which is going to have order p, So we can find some H that is in G, but not this cyclic subgroup. Suppose that G to the A equals H to the B for some A, B in the integers. Then, since the integers mod P is a field, there exists some B inverse in that field such that B times B inverse equals 1 mod P. Then G to the A B inverse equals H. So H is in the subgroup generated by G, but that's contradicting this. Therefore, these two subgroups have a trivial intersection. Now, since G is abelian, these subgroups are both normal subgroups of the group. All elements of these groups commute since G is abelian. Therefore, by the direct product theorem, we have that G is isomorphic to the direct product of these two subgroups, which is just the cyclic group of order P cross the cyclic group of order P. And those are the two options